Okay, so, thank you. Today, we want to look at the mathematics we've already looked at, but this time, we want to try and implement it in Rust. That's why I've said we are implementing it in Rust. So the good thing is that we already know the mathematics. So in other words, the codes will easily understand the codes because we already have the mathematics. So that okay, I'll bring the codes and then we'll try to explain how those codes function. But we're just revising what we've already done, and this time implementing it in Rust. So we had already looked at the properties of integers, and we had defined an integer and said that an integer, these are just numbers from negative infinity to positive infinity. These are the numbers. So these are the integers. Now, so we look at the properties of integers and try to implement that in Rust. So the properties we'll be looking at is a property of prime numbers, divisibility, unique factorization, and the greatest common divisors and the LCM. And all of them will try to implement them in Rust. And of course, we'll do the other topics we've already covered, and all of them, again, we implement them in Rust. Now, so just as brief introduction again of divisibility and what we mean by a number being divisible by another one, or what do we mean by when we say that A divides B? When we say that A divides B, we mean that A can go into B and there'll be no remainder. That's what it means. For instance, 2 divides 4. No, 2 divides 8. And the reason is we can find a number which, when multiplied by 2, the result will be 8. That's what I mean by a number divides another one. So, and that number A is supposed to be non-zero. So we say that this A non-zero and non-zero number A divides B if you can find another number C, which when multiplied by A gives us B. Good, so we already looked at this. And so we want to see if we have bigger numbers. And so then I bring in the code, Rust code, if you have bigger numbers and want to divide. Of course, the ones we've looked at in this example 1 are smaller numbers. Those ones a calculator can do. So suppose we are given a number like the one I have here. I don't know whether you can see this code or whether it's too small, but the number that I have is A here. It's a very long number up to this point. And we want to divide that by a B. So we can use Rust code. And that's what I want to look at. So I'll show you the code here. Then we'll run and see whether it runs and whether it can do division for bigger numbers. Of course, the code, you can always improve it and have it run faster. Although the one I have is okay, it runs okay. Now, so let me just try to increase so that the font, make it wider so that I can see also. Are you able to see?
Yes, yes.
It's okay. So the libraries for this Rust code, my libraries are here, these two. The first one, it handles larger integers. It's to help us handle larger integers. And then the second one, it will offers methods that we shall be using for integer operation. Now, so this code, what you are seeing in bold, dark, that is the code. And then what I've made faint, those are just nodes that will be assisting you to understand what is happening. So for instance, in this case, this is the library, but these are my additional nodes just to help you understand why I put it there. For instance, I've said this library here will be, we've imported that to assist us deal with large integers. And this one will assist us in methods of integer operation, such as division and remainder. So because we want to have a number dividing another one, so it's this library that will assist us to do that division and then give us the remainder. Now, so the main part is this, it begins from here, the main part, and of course you've been learning Rust, so I think you know Rust more than I do, but so we will discuss. Now, so what we do here, the first thing I do here, I give a larger number that I want to be divided. So I'm just telling what I want. I want this large number here divided by this other large number, for instance. Now, so what follows is this part. So I've said what is in bold is the code, but what is in what I put in faint, what is faint here? Those are just my additional notes. So what follows is this part. What is this part? What this part does is what I've noted here. I've said that now we enter the pass the numbers as big unit. So normally this number is very huge, so it's like a string. And then what happens at this point, it's supposed to be converted to a form that the program can understand. And that is what is happening at this stage. So it's just being converted to a point in a language that the program will understand. Now, so what do you see here? I've said pass bytes, large number as bytes, but there's this unwrap. The unwrap, I've said it will handle the potential mistakes. That is in case during when this program is running and then it encounters a mistake during the process of trying to convert this number into a format that the program can understand. If there is a mistake that the program will notice, then it's supposed to stop. It's supposed to stop, so it holds the application. So and then that means the code then fails. It will not give us results. Now, so the first part was just the library, and then the second part is this main. It begins from here, begins from there, and then it comes up to where I've closed it. I've closed it at this point. This is where I've closed it. Now, this part, we are now trying to find the quotient and the remainder. So I've said what is happening in this part, we are performing division, and every time we do division, we note the remainder. So that is what is happening at that point. So the div, and then this rem, which you can see here, begins from here, which you can see here. This div is used to divide by division, and then it will return two things. It will return two things. After division, it will return the quotient and the remainder. So that div, this part is what I've said, let quotient and remainder equal to the number, is a number divided by the divisor. Number divided by the divisor. So when that happens, then it's supposed to return the quotient and the remainder. So that is the part. So I've said let that be that. Then after this part, we print the results. So the result will be quotient and remainder. That's what we want. So when you input this large number here to be divided by this other number, this is what you get. So the output will be that the quotient is this number, also a very huge number. This is the quotient, and the remainder will be 0 for this case. So if our first number was A, and the second number is B, and then we say that B divides A. Now, so I just want to show you this part, the code, and we see it run, so that if you have any question, we can discuss. So let me just go to the visual code. Let me first of all stop sharing that. Then I'll share the visual code wizard. No, that's this part or what? No, it's not this part. Okay, so just a minute. I just want to see how to share that. The visual code. Let me just close a few things here so that I'm left with a few that is okay. So how do I share this visual code?
Then you can share your entire screen.
Yes, I'm doing that.
Hmm.
Let me just again try to. I share the entire screen, but I can't, when I go there, I can't see.
Okay. See it could be on a different workspace. Are you using Windows?
Yes.
For the guys who use Windows, how do you switch workspaces? Could be in a different desktop, so to speak.
Or is that, huh? You can see it, huh?
Oh yes, now we see it, yeah.
It's okay. Let me just try and just a minute. And I discovered that we have programs that cannot run on Windows. So that's something I never knew. Now, so what I wanted to share, what was that? I wanted to show how to divide. Yes, I wanted to show to the program for division. So let me just go there.
And our friends who are masters in Rust, Felix, I think Ken. You can as well also type in or try out the code. Let us know, or just by reviewing, let us know how we're doing. You know, some of us had already implemented the first topics we covered, but I can't see Cecilia and Lynette here. I think Cohen had done it.
It's okay. I think I need to open it fully before I share it. Just need to open fully the program, because when I try to enter in, it's like it doesn't want to.
Yeah, so for the next few days, we'll be again revising, but this time as we implement some of the exercises in Rust and concepts. So we would like to see people building repositories that they can share with the other learners, so we can exchange notes. So we're having implementations of these concepts in Rust.
Okay. Can you see what I'm doing?
Yes.
Is there something you can read from my screen?
Yes, we can see your terminal.
Okay.
You can see your.
You can see the numbers, huh? The number where I'm highlighting. Can you see that?
No, I don't think we can see that.
You can't see the divisor here.
No, we can't. On my side, I can't. Felix, are you able to assist? Ken?
Okay, from my end, I can only see line 76.
Line
76.
76, which one is that?
When you go to your main.rs, the line we can see last at the very top is line 76. We can't see the rest of your code. As
What about now?
Yes.
Can you see anything now?
Now we can see it. Yes, now it's good.
What are you seeing?
We can see your code, we can see your main function.
Okay. Can you see what I'm highlighting?
Yes.
These integers are okay.
Yes.
Let me try to run it and we see. You are seeing what I've written, eh?
Yes, we can see your terminal.
What have I written?
Cargo run.
Bottom. Okay. Can you see the quotient and the remainder?
Yes.
After running, is that okay?
Yes.
Yes. So I just included what you can see here. Those are the notes I was telling you. I have included those notes. But the main thing is this library. And again, I've included some notes here for the library, what each one of them does. Then here is where we now put our large number that we want to be divided. And then this another one, the divisor. Then at this point, now the program has to convert, we have to have the number converted into what the program can understand. And in case there is an error, it has to stop. And then at this point, we have the division taking place, and we are using div underscore rem, just to mean that we want to, this function is supposed to do division and then give us the remainder. And so then we have print quotient and remainder, print quotient and then print remainder. Now, so in this case, there was a remainder. So if there's no remainder again, let me just change the number. Let me use maybe a smaller number this time. I can use one that we know there is no remainder, like 830, for instance. Let's divide this by 5 and see what it gives us. Let's divide this by even 10. Because when you divide by 10, we know that there's no remainder. So let's just run. Let's run this. And when we run, it runs and then gives us that 10 goes into 830, 83 times, and the remainder is 0. So then this is the code for division. That's what we can use for division, of course, with some adjustments here and there. You can have very huge numbers, very huge numbers. When I tried mine with a very huge number, I gave it 3 days and it did not run to the end. So, but the number I put there is also huge because it was about it's about 7-something digits. Let's try another one. Let's try another one and see. Just type numbers there. Just type numbers. Okay, let's also type a division for the divisor here. Let's type numbers also. Okay, let's run and see what happens. Okay, it has gone there, and then there's a remainder. The remainder is also very huge, but it must be smaller than the divisor. In whichever case, it must be smaller than the divisor. Now, so let's look at something else, unless somebody has a question. Okay. So we've looked at that. Oh, so when you try this other number again, when you try this other number C, and then divide by D, using the same code, you'll find that the quotient will be that and the remainder will be this. So in that case, it means D does not divide C. Because by our definition, for D to divide C, there should be no remainder. Like in this first case here, when B divided A, we found the quotient and the remainder was 0. So when the remainder is 0, then we say B divides A. Otherwise, like in this case, then we will say that a D does not divide C. Now, so there's this definition, and I'm defining a prime number and a composite number, and then after that, again, we look at some codes. So if n is a positive integer greater than 1, and no other positive integers besides 1, and n divide n, if there's no other integer other than 1 and n that divides this n, then we say that n is prime. We know what we mean by prime. A prime number is a number which is divisible by only 1 and itself. That's what this definition means. Now, If n is greater than 1, but is not prime, then we say that that n is composite. Is composite. It means it has other factors. It has other factors other than 1 and itself. There are other factors. Now, so what I want to show now is just a code that will assist us to identify prime numbers from a certain point to a certain point if we want. Of course, we know that the prime numbers are infinite. So we cannot say that we can list all of them because we don't know how many they are. They're infinite. So you can just list from this point to this other point. Now, so what I'll be using is an algorithm, and this algorithm is called the sieve of Eratosthenes algorithm. There are other algorithms. Of course, we were supposed to look at primarily testing for prime numbers. We're supposed to do that. We've not done it by calculation. But normally what normally happens physically, manually, if you want to list the prime numbers, you just want to list the prime numbers from one point to another point. Let me say from 1 to 120. What normally happens is that you would check if that number has any other prime factors. That's what happens. So actually, this is what this algorithm will just be doing. This algorithm will check 2, check 3, check 4, check 5 as it goes up to the limit you've given it. Checks every number and sees whether it's divisible by any other number. Let me just show you how it does. Now, so for instance, supposing I've said I want prime numbers between 1 and 144. So this is my main function, then this is the starting point. So I put the starting point is just where I want to have prime numbers from. I want prime numbers from 1 and up to the ending point. I call it 144, for instance, although we will do it with bigger numbers. Now, so what this algorithm will be doing, the first thing it will do is to check. The algorithm will check whether the starting point is greater than the finishing point. The algorithm will do that. It will check if the starting point is greater than the finishing point. This function will terminate with an error message. We'll try that and see. We'll try and have a starting point bigger than the ending point and see what it gives us. So it will do that. And then the other thing this function is doing, after we've inputted these numbers, it will call on this algorithm to compute the prime numbers in the specified range. So this is where it's doing that. Oh, this part is just for the first point. The first point I said that it will check if the starting point is greater than the ending point. It will print, it will see that there's an error, terminate with an error message. So it will say invalid range. The start point is greater than the end point. So that is what it will tell us. Now, so what I've said here is that once you input this, it will call on this algorithm and tell the algorithm, just after it has checked up the start point and the end point, after checking and ensuring that they're okay, it will now call on this algorithm and tell it to compute prime numbers. Let prime numbers equal from the start to the end. from the start to the end. I know that you know what this means in Rust, and you also know what this, if they are double equals, what they would mean. Of course, I'll explain. So this one is just assigning that what is on the right should be equal to what is on the left. So let the prime numbers. So this algorithm should then give prime numbers from the start point to the end point. And then print prime numbers between that point and this end point are, it gives those prime numbers. So that is what it will then print. Now, what is the next step? I've said that this algorithm generates prime numbers within the specified range. If the end of your range is less than 2, supposing you'd said from the range 1 to 1, you see, this range has no prime numbers. This range has no prime numbers. So this algorithm is supposed to note that if your end point is less than 2, this algorithm is supposed to give you an empty vector, since there are no prime numbers fewer than 2. In that range, there are no prime numbers, so it will then give, where there are no prime numbers, of course, it will give you this empty vector. So it will return, this is what it will return. This is what it will return. That is, if end is less than 2, if end less than 2, return empty vector.
We cannot see the screen which you are explaining.
We actually can, Ken. I think could be your side.
Pardon?
Oh,
Alex, can you see?
Yes, we can see your screen.
Okay. So what I'm just explaining what this algorithm, the whole algorithm, what is it, how it functions. How it functions. If you give it a number, if the end is less than 2, the algorithm is supposed to sense that 2 is the least prime number. 2 is the least prime number. Then it will give you an empty vector. Now, this algorithm, at the initialization, what it does, it constructs a vector. It constructs a vector, and this vector that has been constructed is supposed to indicate if an integer is prime. And if an integer is prime, it puts true. It marks it with a true. Now, so you see what the algorithm is doing is this. You've given it start from 1 to 120. It goes, first of all, it starts with the 2, because 2 is the least prime number. After starting with the 2, it then goes to numbers which are divisible by 2. Those are the even numbers. Skips all of them. Skips all the even numbers. And that's what I've said here. It goes from 2 to the square root of the end. The square root of the end. So supposing your end is 144 in this case, the square root of the end. It's running from 2 to the square root of that end. And then for each number within that, what I've just said, I've said from 2 to the square root of the end. For each of those numbers, if the number is prime, it marks it true. It marks it with a true. And then it marks all multiples of 2 with a false, meaning it's not prime. All multiples of 2. So that is what that vector I've said at the beginning. There's that vector which is constructed, and that vector is supposed to be doing that part. So that vector this is where it's doing that. For instance, 0 is not a prime number, so it will mark it false. 1 is not a prime number, it will mark it false. And then for number 2, I supposing this is, and then to the equals to the end. What is that? Okay, let me just read this. If okay, I already explained this, that all the multiples, what is it doing here? All the multiples of 2 marked false because they are not prime numbers. All the multiples of 2 marked false. And then after that, it comes to 3. It comes to 3. Where have I written that? There's a minute. Okay. So what I was saying is it goes from step to step. So supposing it comes to, it began with the 2. So after beginning with the 2 is a prime number. Then it will move through all those numbers, marking the multiples of 2 false, because they can never be prime numbers and are divisible by 2. So all the even numbers are marked false. Then it comes to 3. 3 is a prime number. Now it will mark the multiples of 3 false. It will mark the multiples of 3 false. 4 has already been marked false. So it comes to 5. 5 is a prime number. Then its multiples will again be marked false, and so on. 6 has already been marked false because it's a multiple of 2. So that is what this program does for it to try and list the prime numbers. So if I ask it to give me prime numbers between 1 and 120, then it will give me that. Let me just again go there. Let me just look for it. I just want to open it first of all before I share, because I discover after sharing, when I share and then to look for it, it becomes harder. Okay, so I've opened it. Just want to try and share it now. First of all, can you see it?
Yes.
Yes, so I want us to try and, so this is my starting point. This is where I want to have prime numbers. So let me just say I want prime numbers between, let me begin with 1. Now let me show where the starting point is larger. The starting point is larger than the ending point. So the ending point, let me have it as 16. Let's see what it will give us. So the starting point, we've made it bigger. So let me just say cargo run and see what it gives us. It has finished. It says in valid range, start 120 is greater than 16, which is the end. So we said that will happen if you give a larger start point than the end point. Okay, then we also said that if the end is less than 0, it will give us an empty vector. Let's just see if that is the case. Can you see what it has given us here? Prime number between 0 and 1 are empty. You can see what I'm reading.
Yes.
Yes, let's now give it a range that is meaningful. Let's first of all give it a smaller range, and see what it gives us. 1 to 144. Let's see if it can give us those prime numbers between that range. It has given us the numbers very fast. These are the numbers. The first number is 2, 3, 5, 7, 11, all the way up to 139. Those are the prime numbers within that range. And as we said, it begins with the 2. Then it goes through all the numbers within that range, marking all the multiples of 2 as false. Okay, then it comes to 3. 3 is a prime number. Then marks its multiples false. 4 has already been marked false. So the number that is not marked false is 5. It finds that 5 is a prime number, marks its multiples false, and so on. So that's what it does. Let's give it a big range. Let's 120,000 or even 20 million. 1, 2, 3. Oh, let me just remove the comma. 20 million. That's 1, 2, 3. 1, 2, 3. Okay. What about 30 million? 1, 2, 3. 1, 2, 3. This is a very small number. 30 million. Okay, we'll again try and give it a larger number than that. Let's just see what it gives us. So this one is slightly large. So it's going through all those steps. You can see it's running now. It had to go through all those steps. Then it runs all the numbers. They are running. So then after that, it will give us, after it's done. It's now done. It has given us all these numbers up to here. It has given us up to 29,999,000. I think 199. You can see that, huh? You can see all these prime numbers, huh? Can you see?
Yes.
Yes, so those are the prime numbers within that range. Let's just increase our number a bit. Let's add it 2 zeros, then add it 99, so that we want to the end always to be larger than the start point. Run. Of course, if there are very large numbers, it will take a very long time to do that, but these are not large numbers. I think it will run and give us. Let's just wait. So remember the steps that it's going through, all those steps. So I think this will take time because it has to go through all those numbers, marking them true, 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 those which are, and then others false, 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 false. Then after that, now it lists all which have been marked true. All which have been marked true, now it runs them. So if it's a very huge number, I think it will take some time. Let's just give it 1 minute. If it's not through, we can stop that. And then we'll look at something else. But that's how it does. That's how this program runs. So as we wait for it, we can just go through the program once again. The main part, we've said we have to let our start point. We have to have our start point, and then we have the end point. Then we also said that if the start point is larger than the end point, there'll be an error. It will show that it will not print anything as a prime number. It will tell you the start point is bigger. So it cannot be beginning from above coming down. It will tell you that there's an error there. Now, so again, I said these are my notes, those just notes to explain how it works. And then this is what I've been saying, that if the start point is greater than end point, this symbol here means greater. This symbol here means greater. So it says, if start point is greater than end point, print invalid range. Start point is greater than end point. That's what it will then print. And then if the start point is okay and the end point is okay, then it will call this algorithm. It will call this algorithm to now print prime numbers within that specified range, start and end within this range. It will then call it. You can see if it's a very big number, it will take long, but it's running. So if you give it a day or two, I think it will give you the results. Now, so if supposing the start point and the end point are okay, then this is what it will print. This is what it will print. It will print that the prime numbers between the start point, this is the start point, and the end point are, it puts them in brackets. Now, so what I've said that at the beginning, what it does, it comes up with a vector. So that vector, its role is supposed to now go through, beginning from 2, which is the smallest prime number. It will assign 2, 2 will be assigned true, because it's a prime number. Then all the multiples of 2, it will assign them false. But this part is what I had talked about, that if the end point is less than 2, if the end point is less than 2, it will return an empty vector. It will return an empty vector. So what I began explaining is that if it begins with the 2, then the multiples of 2, going step by step, the multiples of 2 will be marked false. Then, of course, it will go to 3 and again begin the same thing. It go to 5 and so on. And so that process is not a short process, especially for bigger numbers. So this one I've seen that it will take long. So if it takes long, what I then do, I want to stop it. So to stop it, I'll just press Control Shift, then Escape. And then there is Visual Studio. I say end the task, and the task is ended. Okay, so let me now share the other one. Because if I stop it the other way and then ask it to run, it will take again some time. Okay, so we've seen that it lists those prime numbers. I've said here you might use the same Rust Code Studio to run for bigger values, bigger ranges. So if, for instance, if you wanted it to give between this and this, then it will give you those prime numbers, and they're here. I was able to get them from that from the code. Now, so what we've just seen, we can also try to make it better. So I've said that this Aristotelian sieve algorithm would be best for generating prime numbers to a few million. Beyond that, then it will not be able to do, if there are so many numbers, if there are huge numbers. So beyond those millions, then you'll require to make it efficient. No, you may require some good algorithms which exist, but some of them cannot run on Windows. Now, this algorithm can be made efficient with optimizations like segmentation and parallelism. And that is what I've done. I've added a code that I've tried to make it a bit efficient. So I have another one which is a bit efficient than the one we've just looked at. So we'll again look at it and compare the two. And now this other one, the libraries are here. So I'm just making it efficient. It's the same algorithm, but now you make it efficient, you add in more libraries. The first library, of course, we talked about it, and we said this one helps us to deal with the larger numbers. Now, so what we've added to this one to make it efficient, we've added in a function. And this function is supposed to determine if a number is prime. The function is supposed to determine if the number is prime. And so, as we already had said, if the number is too big, this number must be put in a format that the algorithm can understand. Now, supposing you're putting number n, supposing the number is n that I've put in. Now, if this n is less than or equal to 1, if it's less than or equal to 1, the algorithm will say it's false. It give it false, because this is not a prime number. 1 is not a prime number. So if n is less than or equal to 1, n number less than or equal to 1 will not be prime according to this algorithm. Now, what about if n is 2? If n is 2, it will return true. It will return true. What about if n is even? It will return false. If n is even, it will return false. That's why I said that, first of all, it picks 2. Then it goes to all even numbers. Because there are multiples of 2, it marks them false, 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 false. Then it comes back, and if the number is 3, if the number is 3, just before that, it then runs. It's running up to the square root of n. That's what I had said. It runs from n, the square root of n, then plus 1. The square root of n plus 1. That's what it's here. Square root of n plus 1. Now take I to be 3 from this point. Take I to be 3 from this point. So if I is less than n, divided, so take, okay, this point is n divided by I, n divided by I. If n divided by I is 3, remember it's 3. It has already marked 3 to be, 3 is a prime number. Now it's going to the multiples of 3. So if any number n divided by I, if it gives you 0, if the result is 0, it means that number you make it's false. It's not an even number. So what I mean here, what is happening here is that I'm taking a number and dividing by 3. If the remainder, that remainder is 0. So if it goes there and then there is no remainder, there's no remainder. That's what this means. For instance, 27, 9, all those numbers that you can divide, they'll be marked false because they're not prime numbers. And now look at this symbol here. This symbol just means that the what is on the left side plus what is on the right side. So for instance, I is 3. Okay, there's this and, which is the and that just and that we learn in computer. It's just the same. This and has several functions. One of the functions is the and that we use in computer when we are talking about is it addition and so on. Now, but what I want to look at this point is I plus 2. I plus 2. That gives us 3, and that becomes is an even number. No, it's a prime number. So you mark it true. So this function is doing that to all through the numbers. Now the function for computing integer square root. So compute the integer. We say that we'll be doing that. We say that this function is the vector there is running from the start point to the square root of n plus 1. So to do that, we are using the Newton method to perform that square root. So what is happening here is you just performing the square root using the Newton's method. Now the main is here. So you set the lower limit and then set the upper limit. Of course, we had said that if the lower limit is larger than the upper limit, then you must get some message, and it will say that that means that range is not valid. Now, but if it's okay, then it will print. But if it's not, then it will not. For instance, in this case, it says print finding prime numbers between this range and this range, between the lower limit and the upper limit. Then it gives this. Okay, if the start point is, let the start point be that. So what is it printing here? It's just printing the findings. The findings. So it just prints this thing, finding primes between this point and this point. So where the first point is the lower limit and the upper point is the upper limit. Now this point is what he said that if it's a very huge number, then that huge number should be converted to a format that the program will understand. So that format is what we call the parallel processing. And then comes here and computes the prime numbers. Then prints prime numbers. Just prints the prime numbers there. Then it can tell you the period that was taken to go through the whole process. So it gives you that period. So let me look for that code, and then again I share it. Now, so what we should do is that you will also go through the whole the program and see, and try to now understand, go through what I've just done and see whether you can understand it. And then, as Alex had said earlier, we shall also try and see if you can do the exercises now in Rust. Okay, I'm just trying to see if I can open it. Oh, was I sharing?
Right now it's blank.
Okay, I'm still seeing the other one that was running for a long time. I think it's still running and is preventing me from opening any other. Just a minute. The other one that we had to put with very huge numbers is still running, and so I'm trying to see how I can stop it. So the problem is if one is still running, I tried to stop it. It's like it never stopped properly. That is why now I want the experts now to tell me how to do this. Isn't it? Yeah, it's okay now. No. Submit. Why is it not? It's running in the background, so it prevents another thing from.
Be Felix be able to assist?
Okay, I'm not able to see your screen.
Yeah, so, okay, let me just share what the difficulties I'm facing. I wanted to open first, then share. Go run. Okay. Go run. Good. What numbers? Oh, I had given it a very small number. It has already run. It has already run, and I gave me the list of prime numbers. So what was my main is down here. I had given it from 20 to 200. Let me give it now from 1 to 20,000. From 1 to 20,000 and see what it gives me. So it was just there, and I was wondering why I cannot see it. You can see it's very fast because 20,000. That's a very. Did I give you 20,000 really? Yes, I gave you 20,000. It has gone up to 19. So these are the prime numbers, and you can see it has given us the time it has taken to do that. That's what we said from this code. It will give us. So this is a bit enhanced than the earlier one. And we've added a few things just to ensure that it's a bit faster. Let's try from 20 million. 1, 2, 3, 1, 2, 3 to 30. How long will it take? 30 million. Another 1, 2, 3. Let's try and see how long it will take to do that. Just said finding prime numbers between this, so it's just going through the steps, just going through the steps. once it's done, it's supposed to give us those prime numbers. And remember, the steps are not few, because it has to mark all the numbers which are multiples of 2, mark them false. Come multiples of 3, mark them false. Then go to 5, then go to 7, and so on. So it's not a very easy thing. But let's see how long it will take. Of course, it will give us time. It will tell us how long it took to do that. I'm trusting it will work, because 20 million and 30 million, but those are very many numbers. Those are very many prime numbers. They are not few. Yeah, if we realize that it's taking a lot of time, we can stop it. But those are very many prime numbers. It's supposed to go through all of them and then give us a list. I think because of time, I can just stop it. Because of time, I can just stop it, and then we look at something else. So to stop it, I just press Control Shift, and then Escape, and then then I go and select Visual Code. Then I say End the process. Okay, let's look at something else just briefly. Okay, and then we bring in another library, and I'll use it in the next example. I just want to show how to factorize prime numbers. Of course, we factorized this way, but we can use an algorithm, and let's just see how to factorize prime numbers. We can even factorize very huge prime numbers. This is the algorithm. I just want to run that one, then, but next time we begin from there. Just want to run the one for factorizing prime numbers. Or just before that, we want to look at one that tells us if a number is composite. Yes, let's just look at one that tells us if a number is composite or prime, because we are very much interested with the prime numbers. For instance, when we are making our key in cryptography, we are very much interested with the prime numbers. So we need to know which numbers are prime and which ones are composite. So that is what I just want to try and see. So let me again share. So the one that we use for telling if a number is prime or not is what we call the Rabin algorithm. So the Rabin algorithm is the one I'll be using to tell if a number is prime or not. And it's here. So I've given it this number. I just want to run this number. This is a very huge number. It's a very huge number. Let's see whether this number is prime. or not, because it's a huge number, we don't actually. But let's run. Runs, and then it tells us this number is composite. It tells us the number is composite. You can see the result there. Let's add there another number. I just want to, or let me remove this and put a 1, see whether it will change. Well, if it changes, it will tell us. Still composite. Still composite. What about if I put a 7 here? Will it still be composite? It can still be composite. Cargo run. Okay, I was looking for a prime number. Let me see if I have 1 in my notes. And then I put it there. Just see if I can find a prime number in my notes. Yes, okay. Just wonder if I can see, not a smaller one, because the smaller ones, there are so many. I want a large prime number, and I want it to tell me that the number is prime. There's one that I had. There's one that I had. Okay, I can't see it. But let me try this one. I've found another one. Let's try. Is that? I'd stop sharing, or I'm still sharing.
Yes.
Is it still visible?
Now it's not.
Oh, I've just stopped. Okay, what about now?
Yes.
You can see it, huh? Yes, I want to change this number. I just want to change it to another number, and let's see whether it tells us that it's prime or not. Let's have cargo run. Oh, just a minute. What is the error here? Just a minute, just a minute. Okay. There's something I've done, or oh, is this space? Okay, so let me again do it. It was that space. I put a space. So it was seeing that space as a number. So it has now run and is telling us the number is probably prime. You see, you can never say that a number is definitely prime until you perform several tests on it. So every algorithm you use, it will tell you it's probably prime. And whenever it tells you it's probably prime, the chances of it not being prime are very minimal. Very minimal. Let's try a smaller number that you know. Let's try 29. Smaller number. This one we know what it is. What happened? Have I put a space again or what? Just a minute. I think there's something I've done, but I cannot notice what it is. Did I add some? I think I added something there. Okay, let me just change it. Just a minute. No, but because of time, I think I should just stop there. But that's how it works. I'm trying to see what a mistake I've done. You see, the problem with this thing, you cannot go back to how it was. I think you are the experts. You'll try to to educate me more there. Thank you.
Thank you, Dr. Sakwa. As well, thank you for